Yeah, yeah. Let me. I'm trying to find my. There we go. Okay, hold on. Where's the? I got to start the lesson. I get so confused.
Okay, so it is Tuesday morning, and Mr. Bouchard is confused, which is, you know, that's a good sign that everything is normal. So here we are, biology class, period 3, and we're going to be talking about water properties. I know you've done some stuff on that already, but we're going to pull it all together in a paradigm Mr. Bouchard's going to show you in a minute, just to make sure you got everything straight before we go on to organic chemistry. So that's going to be the second half of class. So it's really great. Those of you who have been keeping up and doing all your work, really want to give you big kudos in this environment. I know that that's been difficult for some people, and you guys are really doing well. If you are a little bit behind, if you're having trouble catching up, or you have some things that you're having trouble doing, you should go and see Mr. Bouchard in his breakout room today and make sure that you have caught up with all of your work. Make sure that you've done like the coloring water molecule, which shouldn't be hard. You should be able to do that, and that you've done the ed puzzles, and that you're all up to date on all the big labs and things. So go see him about that, and if you're all set with that and you're ready to go forward, you'll come see me and we'll start talking about organic chem. Okay. So Mr. Bouchard, you are on.
Oh, did you want to talk about the coloring thing first?
Well, you guys, I mean, I showed them that. I did show them that, but you show them again?
Oh, I can. Okay. No. I was just confused. Sorry.
This class got the good version. You guys got the good version, right? Where you saw the PowerPoint, and I showed you how to color it in. So you should be okay. If you're not okay, I think Mr. Bouchard could even show you that too.
Yeah.
Right.
Okay.
So I think they're ready for their. Yeah.
All right. Chrome tab.
For you to be brilliant with them. Go be brilliant with them.
I shall. Here we go. There we go. Go ahead. Let's go into joinpd.com. Type in that code. I should see a bunch of you lovelies start appearing in there. Looks like we got 3 of you. We have 17. I got 3 more. I'm going to give you 1 more minute and we'll get started. 1 minute. We're working on those other things, Miss Murdoch. I had to close out and redo add-on for the questions. So that's why it took me a second. I was like, why does it just keep giving me the circle of death? All right, we're going to get started. If you have a question about it, you can go into Join PD. So we're going to talk about water today, guys. Water is huge for us as land dwellers. Our body is made up nearly 70% water. Your cells are filled up with nearly 2/3 of their mass is water. And you're also surrounded by water. Your cells, everything. You guys, water is crucial to our survival. If we don't have water, we die faster than if we don't have food. That's how crucial water is to our survival. Water is the medium in which most cellular events take place. Water also helps move nutrients and other substances into and out of your cells. Its unique properties are due to the chemical nature of its structure. Explore properties of water, apply the properties of water to real life. Oh, sorry. I just read on those things. Oh, I just got into a brain fart for a second there. So what I'm going to do is I'm going to share this. So I'm going to have to restop sharing. Sorry. I'm going to play. Give me a second.
Writing's not that
I got to
easy,
wait for this
but
Grammarly
Grammarly
commercial
can help.
because I had to restart everything.
Chemical bond.
All right. Now I'm going to share this. So just another screen with you guys. Chrome tab, type schema bonds, share. Should come up. Excellent.
The interactions of two or more atoms mainly occur at the outer shell or energy level. The consequence of these interactions results in a chemical reaction. In atoms that have fewer or more than 8 electrons in their outermost energy level, reactions occur that result in the loss, gain, or sharing of electrons with another atom to satisfy the octet rule. The octet rule means that elements tend to combine so that each atom has 8 electrons in its outermost shell. This results in the formation of structures such as crystals or molecules. There are two main types of chemical bonds: ionic bonds and covalent bonds. Ionic bonds are bonds where the transfer of electrons takes place. Let's see how this type of bond works. Here we have a sodium atom, which has an atomic number of 11, meaning it has 11 protons in its nucleus and 11 electrons in its shells or energy levels. Shell 1 has 2 electrons, Shell 2 has 8 electrons, and Shell 3 has 1 electron. And here we have a chlorine atom, which has an atomic number of 17. So 17 protons and 17 electrons. It has 2 electrons in shell 1, 8 in shell 2, and 7 in shell 3. We know that atoms want to have 8 electrons in their outer shell. So sodium can give up 1 electron, and now it has 8 electrons in its outer shell, and chlorine can take that electron from sodium, and that will give it 8 electrons in its outer shell. Since the sodium atom gave up an electron, it has 11 protons, which are positively charged, and 10 electrons, which are negatively charged. This results in the formation of a sodium ion with a positive charge. An ion is an atom or molecule with a net electrical charge due to the loss or gain of an electron. Since the chlorine atom gained an electron and now has 7 protons and 18 electrons, it is a chloride ion with a negative charge. The positively charged sodium ion is now attracted to the negatively charged chloride ion, and NaCl, or table salt, is formed. This is an ionic bond. So ionic bonding is when an electron transfer takes place and generates two oppositely charged ions. Now for covalent bonds. Covalent bonds are chemical bonds that are formed by the sharing of one or more pairs of electrons by the outer energy levels or shells of atoms. The 4 major elements of the body, carbon, oxygen, hydrogen, and nitrogen, almost always form covalent bonds by sharing electrons. So, for instance, 2 hydrogen atoms can bond by sharing a pair of electrons. Hydrogen is one of the exceptions to the octet rule of having 8 electrons in the outer shell because it only has 1 shell. Let's look at carbon dioxide, or CO2, which forms the covalent bond. Oxygen has an atomic mass of 8, so 8 protons and 8 electrons, 2 electrons in its inner shell and 6 in its outer shell. So oxygen atoms want 2 more electrons for their outer shell. Carbon has an atomic mass of 6 protons and 6 electrons, 2 in the inner shell and 4 in the outer shell. So it wants 4 more electrons for its outer shell. These fellows can make each other happy by sharing what they have. Oxygen atom number 1 can share 2 of its electrons with the carbon atom, and in return the carbon atom can share 2 of its own electrons with oxygen atom number 1, making oxygen atom number 1 happy. Then oxygen atom number 2 can come in, and like oxygen atom number 1, it can share 2 of its electrons with the carbon atom, and again in return the carbon atom has 2 more of its own electrons that it can share with oxygen atom number 2. So now all 3 atoms are happy. By sharing 2 pairs of electrons in this situation, a double bond has been formed, and double bonds are important in chemical reactions. And that be the basics on attraction.
Give me 1 second. I'll go back and reshare my screen. I just closed that one out this time. Last time, guys, it started talking halfway through my presentation. I was like, what's happening? All right. So, and here's the code if you ever need it right up here. All right. So water is a polar molecule. What other things have you ever had or you played with as a kid that had something described as having 2 poles? What would that be? Something you played with as a kid that you think about that? Magnets. Yes, Sarah. Brilliant. Well, with magnets, let me ask you this now. Why do they have 2 poles, Sarah? What's the difference? Wait, or anybody else who knows? Why do they have 2 poles? What's at one pole and what's at the other pole? North and south, yes, not that kind of. But what about the ends of the magnet? What's different about them? Positive and negative. Yes, Catherine. Excellent. So water molecule has a positive end and a negative end. And that's why it's called a polar molecule, because it has 2 different charges. And this is very important for its survival. Or not for its survival, for its properties and why it's so valuable to us and to life on Earth. All right, so the electrons are not equally shared. This is what makes water polar. It's sort of like negative, positive, one end. I always think of it like a tug of war. So like one end positive, one no negative, no positive. And the covalent bonds hold them together. The oxygen end is partially negative, and the hydrogen end is partially positive. All right. So drag your dots to the end of the water molecule, to the negative end of the water molecule. Let's see it. I'll give it a second. Looking at that picture, pay attention. There's a little clue in that picture. There's a little clue. Oh, yeah, it looks like we're all getting those chicken pox up there. We're getting those chicken pox. Yes, at the top end, the oxygen end, the negative end. And you'll usually see that depicted with these little negative signs. Okay, excellent, 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 excellent. Good job, guys. So, water and hydrogen bonding. There's 2 things. Water is both cohesive and adhesive. Cohesion means water molecules will stick to each other because, remember, we just talked about water molecules having positive and negative ends. So they can stick together, stick to another water molecule and another one. That's called cohesion. However, water molecules also can stick to other things, which is why we see that bend in the meniscus, because sort of the water molecules are crawling up the sides, and that's what we call adhesion. And I always think of it like adhesive for your Band-Aids, because it's sticking a Band-Aid to your skin. It's 2 different things. So when water sticks to something else, it's adhesion. When water sticks to itself, it's cohesion. All right, let me go on. There we go. Now, some of these reasons for this cohesion and adhesion. Surface tension. If you guys have ever seen those water striders, those are little bugs that can run across water. And by the way, this summer I found out spiders can run across water. It is petrifying. It happened to me while I was doing my lap swim. They came out of the little side things, and I was like, oh my God! Because it was in the morning. I was the first person in there. I'm trying to do my laps, and all of a sudden I look over and I'm like, woo! Big spider. I'm like, no. Yeah, I know, Ariana, right? And then there's this other thing that's very important that plants do. It's called capillary action. And what capillary action does is allow water to travel up the veins from the roots up through to the tree limbs and then out. And that's how water gets up to the plants, through the roots, and that's called capillary action. It sort of climb on each other and get their way up there. Drag a dot to show water's surface tension property. Which one of those shows water's surface tension? Let's see, I got how many people responding? 8. I know there's more than 8 of you in here. Let's see. Okay, show responses. Oh, sorry. Be careful. Surface tension is this one. Very good. Capillary action is where it comes out the roots and out the plant. Surface tension allows things to spread out. Now we, as humans, cannot have surface tension. We are not very buoyant. We just sort of smash through it. Smash, smash. Hulk smash. But when I get in the water, I'm rather buoyant, so I just sort of start floating there. That's what Miss Murdoch says to me. I'm a very emotional person. She makes me all the time. It's very sad. Oh, sorry, wrong thing. Now which one shows capillary action? Let's see. We got 14 out of the responses. 15. I know there's more of you out there. That means 5 of you are just ignoring me and have gone away from your computer. Oh, I am hurt. Come back. Come back. Yes, capillary action. You, this Lone Ranger, you need to come over here. Yes, good. Capillary action again. That's very important to plants and their survival. Because again, all living things need water. Every living thing. All right, water's resistance to temperature change. This is huge, huge for our environment. All right, water expands when it freezes. Water is less dense in solid form, so ice floats. Why is it important for ice to float? What would happen if ice didn't float? Somebody put it in the chat. Looking up at the chat, I see nothing. Lakes and ponds, the fish would die. Yes. Because the animals would die because the lake would just sort of flush and kill everything. And then you wouldn't have survival because when ice floats, yes, death. Death and carnage. There would be no life in the water. Exactly. Now, another part about water's resistance to temperature change is it absorbs heat when it's evaporating. This is very important for our planet because if it didn't do that, the sun would just fry up all our water. We wouldn't have any. As humans, when we sweat, it helps lower our body temperature. It's our way of maintaining homeostasis because if you didn't know, humans need to maintain a certain body temperature. So when you, for instance, when you sweat, that's your body's air conditioning system, sort of like trying to bring away the heat away from your body. And it's very bad when your temperature rises. That's why when fevers happen and fevers get large, it impacts the body's functioning and enzymes start not working right. And we'll get into enzymes soon. But things start not working right when temperatures increase. All right. Next one. Water is a universal solvent. So like dissolves like, and polar and ionic substances easily dissolve. The solute is a substance being dissolved. The solvent is the one doing the dissolving, and the total thing is the solution. So I go home, every morning I have a cup of coffee. I put sugar in my coffee. What is the solute and what is the solvent? Looking in the chat. Looking in the chat. Water is what? I was yawning. What I said, so let me repeat that. Sugar, I put sugar in my coffee. What is the solute and what is the solvent? Sugar is solute. Yes, Iman. Sugar is the solute. It is what is being dissolved. My coffee, you could say water is a solvent because water basically is coffee, just with the grains of it. But I get what you mean. I'll give you that. I'll give you that. So sugar is the solute, though. Good. How many of you, have you ever been to Luray Caverns, any of you guys? Anybody here ever been to like the Luray Caverns or the caverns in the Bahamas? Yeah. So when you see, if you ever go to the caverns, yeah, you can see sometimes it'll show you like the donut rock. And I'm a large man, so whenever they say donut rock, I'm like, yes, it is beautiful, Ariana. But I'm like, the donut rock. Oh, I'm so hungry for donuts. I'm stuck in this cavern. But the donut rock is the one where water just kept dripping on one spot and sort of dissolved its way through the rock after millions and millions of years. And that's why water is a universal solvent. Sooner or later, water will break it down. It may not happen in any of our lifetimes or way, way long, but after a while, it sort of happens if it constantly has that water base. All right, let's see what we got next one. So water and pH. Water molecules have the ability to naturally dissociate into hydrogen ions, and hydroxide ions. Acids have strong acids have a pH of 1 to 3, and they contain hydrogen ions. While strong bases tend to have a pH of 11 to 14 and contain a lot of hydroxide ions. So if I say, all right, we go and measure two substances. One substance has a pH of 3, and the other has a substance a pH of 5. Which one is a stronger acid? pH 3 or pH 5? pH 3, yes. Further you get down the pH scale, the stronger it is. While the closer to 7 you get, the more neutral you are. And water generally falls within the neutral setting. Good, good. Now, on your dots, we have over here normal rainfall, pH of 6, toothpaste, pH of 8, and blood, pH of 7.4. Using your dots, put the red over the acid, put the green over the neutral, and put the blue over the base. I'll give it a second. I see 2 responses, 5, 20. Let's see. Red over the acid, which is a 6 up here. Blue is the base, and then green should be down here. Oh, Lord, we got a lot of chicken pox going on this screen. Oh, no. All right, now water and density. Density is a measure of how close and how far apart molecules are in a substance. Ice is less dense than liquid, so ice flows. This is important for ponds, lakes, and temperate regions, so they don't freeze solid in the winter. Well, yeah, water. Miss Murdoch, did you want to answer that question by Luke in there?
All right, yes, I'm sorry, what was the question?
Is blood neutral because it has a lot of water in it?
Yes, your blood is, it's actually slightly basic. 7.4 is actually a very precise number. If it goes higher than that or lower than that, you will feel it. You can get really sick really fast if it moves anywhere away from 7.4. So yes, you definitely want to have blood that is close to neutral. And mostly, yes, you're right, because most of your blood plasma is water. There's a lot of water in your blood. What makes it look red are the red blood cells that are floating in it. And red blood cells have a chemical called hemoglobin that we'll learn about a little later. That's a protein that has an iron atom in it, and that iron makes it look red. But most of your blood is water. That's absolutely right.
Excellent. So so drag your dots to the less dense form.
Remember, density is about the spacing, how far apart molecules are in a substance. So which picture shows you molecules more spread out, less close to each other? That would be the less dense diagram.
Let's see what they say. Let's see your responses. Yes.
Yeah.
Good. Hydrogen bonds. Look how less dense these are compared to these. These guys in here, this looks like a pre-COVID experience. This is post-COVID experience.
I'm not sure I understand the metaphor.
Because they're all bunched together. Density.
Oh, you mean in terms of people?
Spaced
People
out.
with their spacing and distancing. Ah, I got it now. I got it. That's very good.
Thank
Yeah,
you.
before COVID, we didn't mind close to each other, and now after COVID, we're very spread out. That is genius, Mr. Bouchard.
Thank you, Sarah. Extra A for
Fun
you.
real life application. That's awesome. Awesome.
All right. What I want is a little break. Miss Murdoch will play some tunage.
Yes, go and dance, baby.
Every day you crawl into the night, a fallen angel with your wings set alight. When you hit the ground, everything turns to blue. I can't get through the smoke that's surrounding you. Just when you're falling, I can't tell which way is down. And when you're screaming, somehow I don't hear a sound. And when you're seeing things, and your feet don't touch the ground. Just when you're falling, I can tell which way is down. I can see through the clouds. I can walk right through the walls. Hang me out to see me, but I can't take the fall. Should I cross the river when I may get swept away? Out there on the water, you can still see me wave. Just when you're falling, I can tell which way is down. When you're falling, what's good? I can tell which way is down. Love you, love me. I can see all don't touch the ground. 'Cause when you're running, I can tell which way is down. And when you're screaming, somehow I don't hear the sound. And when you're seeing those things, don't touch the ground, don't touch the ground. When you're falling, I can tell which way is down. And when you're screaming, never hear the sound. And I hear the sound, and hear the sound.
I can tell which way is down.
rhythm. Singing this rhythm when you're screaming. Somehow I don't break this rhythm. Singing something you love. Singing something you love. Singing something you love. Singing something you love.
I'm coming. Right Okay, break's over. Now we should be ready to go into breakout rooms depending on what you need to do. So if you're ready to go on into organic chemistry with me, because you got everything else done, then come with me. If you need to ask Mr. Bouchard some questions or catch up on other things, you go to Mr. Bouchard. So,
If you have everything, I'm going to kick you over there. If you don't respond to me, I'm kicking you over there because we need to learn what he's doing also. And my room is just not a room where you just sit there and do nothing. So if I call your name while Ms. Murdoch is setting this up and you don't respond to me, I'm going to at least hope you learn by osmosis by me throwing you to Ms. Murdoch's.
you
Because
also don't want to come to my room and do nothing because this, today, what we're going over is the first part of the really difficult stuff. It's not an easy unit. So don't come to my room and not pay attention. You need to pay attention to this. Okay, here we
all right, let me go into grade books. Yeah, some last time didn't even have anything to make up, so I just started dragging them up to you. I'm like, why are you in here?
It's actually in good shape, so you can kind of gauge it there.
Yeah. All right.